The last video for our first week on computation and unit number 2 is going to cover days 4 and 5, the difference between and what are rational and irrational numbers. Now I have some charts made up here. First, to describe what rational and irrational numbers are, let's be very clear. All we're doing is classifying numbers like you would classify rocks in science class. We're going to look at the number, we're going to look at the characteristics that it has, and then we're going to simply decide, is it rational or is it irrational? And let's be very clear. Numbers can only be one or the other. Since in PA Core 8 and most of Algebra 1, which is next year for most of you, the numbers we're going to deal with are what are called real numbers. Now, real numbers, if you imagine every real number contained inside of this rectangle, the rectangle could be split into two groups of numbers. The rational group, which look all like ratios or fractions made up of positive and negative whole numbers, and we call those integers. And then there's irrationals. In irrationals, you'll notice there's no fractions over here, but there's some strange symbols which you've seen before, some radicals, square roots, cubic roots, and some numbers that don't look very nice to work with like we'd expect. So today the video is all about rational numbers, and the definition of irrational, interestingly, is, while we could describe it in a couple different ways, it is any real number, which is everything we're going to work with in PA Core 8. So it's every real number that's not rational. So if you simply figure out what rational numbers are, and you run into a number that's not this, it must be this. So it makes it easy if I give you a list of numbers and you have to identify which ones are rational or irrational. Again, if you can pick out the rational ones, whatever's left over will be considered irrational. So let's go ahead and focus on these 4 different examples of what rational numbers are, and let's clarify what rational numbers are. So first, rational numbers are any number that can be made into the form a over b, so long as a and b are both integers. And integers are whole numbers, like 2s and 5s and 7s and 10s, but whole numbers also include the number 0. And to make them integers, you can include the negative version of all of those. So not only 2s and 5s and 7s and 10s, but the negative 2s and negative 5s and negative 7s and negative 10s. So that tells me this negative right here doesn't scare me off at all. And the fact that these are not negative doesn't scare me at all. I also recognize that each one of these has a form that looks like this. So we're in great shape. These are all examples of rational. So let's clarify that if you see any fraction, even if it's improper, and you see 2 examples here, even if they're improper, they are automatically rational. Now let's stick with, I guess we'll stick with the common color here. Let's also realize that 3/4, you could probably tap into your previous knowledge. You know that 3/4 is the same as 0.75. What that tells me, I think, is if 3/4 is rational, this must be rational also. And that brings us to our first piece. This is called a terminating decimal. And a terminating decimal is simply a decimal that has an end to it. So there's no other numbers after this. I suppose you could add a bunch of zeros, but I don't know why you would bother. So this fraction can be made into a terminating decimal. And if it's a terminating decimal, it is rational. So now we have 2 different forms. Anything that can be in this format or any terminating decimal. Either of these 2, if you see them, are rational numbers. Now let's go down. I could make this into a decimal also, but for our purposes right now, let's go ahead and make it into something that's a little different. I could turn this improper fraction, 8/3, into 2 2/3. And if this is rational, then so is this. And that tells me, you guessed it, that mixed numbers must also be rational. So now we have regular fractions, I'm calling them regular. We have terminating decimals, and we have mixed numbers. Any of those are examples of rational. Let's go to our next example. This is a normal, whatever normal means. This is a proper fraction. It happens to be negative. That doesn't scare us. The only thing I can really do with this one is turn it into a decimal again, but it will be different than this decimal because this decimal, negative 0.66666, repeats. That's what these 3 dots indicate, that it continues on forever. And the fact that we see a numeric pattern here means it's a repeating decimal. You would have seen something like this in the past. which would be a perfectly acceptable way to write this. And let's go ahead and write it with words as well. And what, once again, you should recognize is that we have multiple different variations on, and if this is one of the variations of rational numbers, then repeating decimals must also be rational as well. And that gives us our last piece. This is once again an improper fraction. Now, it would be weird to have two of the same example here, but I did it this way because when I get a number 4, 4 is a whole number. And I could be more precise, it's technically also an integer. And, oops, I'm not spelling correctly here, sorry. integer. So if you see a whole number or a natural number or an integer, any of those kind of what I'll call whole values or integer values would all be considered rational. But I left myself a little bit of space, and I'm even going to change color because I want you to recognize this. 4 is the same as the square root of 16 because the square root of 16 is 4. What that tells me is if I have the square root of a perfect square, that is also rational. And you can probably guess that I could do another thing with this. I could do a cubic. The cubic root of 64 is 4, and that tells me that perfect cubes, when taken to the cubic root, are also examples of rational. And that's as far as we're going to go. Surely we could do more indexes than 2 and 3, but I think that summarizes things. And with that in mind, I want to bring back the previous kind of page. This would be a good one to pause on and make sure you record that these are all of the different types of rational numbers. And then let's go back and talk about how if it's not this, then it must be something else. So rationals can be whole numbers, integers, perfect, the square roots of perfect squares, the cubic roots of perfect cubes, terminating decimals, repeating decimals. Irrationals are simply numbers that aren't this. So what you'll notice over here are you will see square roots, you will see cubic roots, but you notice that the 17 and the 24 are not examples of perfect squares. So they're not this. Cubic root of 31, that's not a perfect cube, so that is not rational. And finally, pi. Pi is so famous. Pi is interesting because pi is actually built by a ratio of two values. Pi is actually the ratio of circumference to diameter of a circle. However, pi, I want to make sure this doesn't clutter up anyone's mind though. Pi is that really crazy number. It's like 3.14159. I hope I'm not getting this wrong. But what I remember is that it continues on forever, but there's no pattern to it. So this is what we would call, and I'm going to say this, but I'm not going to write it down for speed. If rational numbers can terminate, pi is an example of a number that is in fact, I will write it down. Non-terminating. In fact, I guess what we're doing is we're defining irrational. Instead of saying not rational, we're going to say what rational numbers are, and then we're going to say this isn't. So irrational numbers would be non-terminating and, interestingly, non-repeating. Right? This was repeating, 2 2/3. This was repeating, 0.6 repeating. This is non-repeating. So irrational numbers would be decimals that never end. That's what non-terminating means. Non-repeating doesn't mean there's not dots. It means the pattern doesn't repeat. And that's that. So when you look at lists of numbers, think about what's on the inside of the radical symbols, if there are any. Think about your different variations on your fraction or your ratio, and make a good decision on what rational and irrational numbers are.